It is my pleasure to welcome our next speaker, Devendra Chaplot, who recently joined Mistral AI, coming from Meta AI. So anybody who works in embodied AI navigation knows Devendra really well. He has been influential on introducing modular architectures for navigation with works like active neural SLAM, semantic exploration. He has worked on many different learning algorithms like RL, imitation learning, and Jan will be happy that there is a paper called No Simulation, No RL, which he also authored. So Devendra has also been really influential with the Habitat platform, which which is really heavily used in navigation. He has won many awards and probably more important, many challenges in navigation, and he's also organizing challenges. He's one of the organizers of the recurring embodied AI workshop, and we are especially happy to see him here today, where he will present a new paper which he archived yesterday. So Devendra, the floor is all yours. Thank you.
It's working. All right. Thank you. Thank you. Okay, so this is a video from May 2019, when I was still a PhD student at Carnegie Mellon. And a lot of people told me not to do robotics. Marshall has a saying that every time you touch a new robot, you extend your PhD by 1 year. And I was trying to get simple navigation policies to work on the robot. And here we were just trying to get the robot to avoid obstacles, avoid this red chair and move past it, but we were having a hard time. And in my PhD, I really wanted to build a universal navigation system. And what do I mean by a universal navigation system? Well, we want our navigation system to be multimodal. We want it to reach any object specified in any way. It can be specified using an image. You take out your mobile phone, take a photo, ask the robot to go there, or you can describe the goal object in language. Say, find the fruit basket on the kitchen counter, or a category like a cup. We want it to be lifelong, which means that we want it to have a lifelong memory. We want it to remember locations of objects. We want it to remember its environment and improve over time. And we want it to be platform agnostic. If it's a universal navigation system, we want it to work on any mobile robot with a simple set of camera and pose sensors. And today, I'm going to talk about our latest universal navigation system. And this is an example of what it can do. So you can start the robot in any completely unseen environment, like this home. And you can ask it to find goals specified in any way. So for example, here the goal is an image of a sink. So you can take any image from any viewpoint, any camera. It doesn't have to be robot specific. And the system can explore the house. And as it's exploring the house, it builds a semantic map of the environment. It keeps a track of all the objects it's seeing. And once it sees the object, it goes there. And then you can keep giving it new goals. So now the next goal is the red cup on the brown leather chair. And the robot keeps exploring, finding new goals. And here we gave it a new goal, this image of a couch. And the robot has already seen that couch in its previous experience. So it can, instead of exploring again, it can directly go to that couch, as shown in this green object on the map. And then you can keep giving it goals, like there's another goal of the bed. So robot finds the bed. Then you can ask, oh, go back to the kitchen sink. But this time we are asking it in language. It already knows where the sink is. And it can also you can combine this universal navigation system with picking and placing skills. So you can ask it to go to this teddy bear, pick it up, and then go to a chair and place the teddy bear there. So today I'm going to talk about our latest universal navigation system called GOAT, or Go to Anything. And this is basically a consolidation of all our research in the last around 4.5 years. We have put together all the learnings that we did on navigation and put it together in this one system that is able to go to any object specified in any way in completely unseen environments. So let's start with defining the problem of navigation. So it's very easy to define. You have a robot operating in an environment. It gets observations, and it's taking actions. And the objective is to reach a specified goal location in the environment. And specifically, we will tackle a very general and challenging variant of the navigation task with minimal assumptions. The robot starts in a completely... All right, so we'll tackle the most general and challenging variant of the navigation task with minimal set of assumptions. So we have a robot starting in a completely unseen environment. It has no experience, no map of the environment. And it's asked to navigate to an object, let's say a toilet. And it has only access to an RGBD camera and a pose sensor. And it has to take actions to reach the goal object. And so in order to do this task efficiently, you need to have certain capabilities in the navigation system. So first of all, it has to have some spatial scene understanding to detect what areas are navigable and what are the obstacles. It has to have some semantic scene understanding to understand the objects around it. It needs to have some semantic exploration priors. So in this case, where is a toilet more likely to be found? We know that going into the hallway is more likely to lead to the goal and rather than the dining room here. And as it's exploring, it needs to have an episodic memory to keep a track of what object it's seen and what area is explored and what is still unexplored. And while it's exploring, if it sees the object, it has to actually go and navigate to it. So we have this navigation task, completely unseen environments with simple input sensors, camera and pose, and output actions are simple low-level navigation actions. And there are different ways of specifying the goal. It can be a point coordinate, it can be images, objects, or even language. So the problem of navigation is, of course, a very rich history. It has been studied for more than 3 decades. So this is a very early navigation system called Rhino. It was developed by researchers at CMU and University of Bonn back in 1998. And so this was the first robot that gave museum tours. And it was based on a classical navigation pipeline where a map of the museum needed to be pre-computed. Then the robot would localize using LiDAR or sonar scanners. And then there was a path encoded in the robot, which the robot followed to give the museum tour. And in last few years, there has been a lot of work on training navigation policies using end-to-end reinforcement learning. The idea is very simple. You give the robot positive rewards for reaching the right location and negative rewards for reaching the wrong location. You take the raw observations, pass it through a neural network, predict the actions, and use the reward to train this neural network. And so these two classes of methods have different properties which lead to different strengths and weaknesses. The classical methods are modular. They have explicit memory, which can be very useful for mapping and planning. And they have a rule-based policy. This leads to very good spatial understanding of the environment because they are using depth sensors to build a geometric map. They are also very good at long-term memory and planning because the explicit map stores all the points you have seen, and it can be used for planning using analytical algorithms. But they lack at semantic understanding and generalization. And on the other hand, end-to-end learning-based methods, they have implicit planning and memory with a learned policy, which leads to very good spatial and semantic understanding and generalization capabilities, but they struggle at long-term memory and planning. because of high sample complexity in exploration. And so we define this class of methods which we call modular learning-based methods. And the idea is to combine the benefits of both classical and end-to-end learning. Specifically, we will have modules borrowed from classical literature, specific modules for mapping, planning, and goal localization. And in each of these modules, we will use learning to get generalization capabilities. So I talked about all these different types of navigation tasks: point goal, image goal, object goal, language. And in all of these tasks, one of the common capabilities you need in a robot is to explore the environment in order to find the goal. If you're in a completely unseen environment, the robot does not know where the goal is, and it needs to explore a new environment. And we built this system called Active Neural SLAM to solve this exploration problem. So this is a modular learning system where we take the observation and the pose reading, and we pass it through a neural SLAM unit to get a map and a pose estimate, a refined pose estimate of the robot. Then we pass it through a second module called the global policy, where we have a long-term, which predicts a long-term goal, which is basically a point coordinate on the map. And then we can use analytical path planning to plan a path to this long-term goal and have a local policy, which is the third module, to take actions to reach this goal along the path. And this is what it looks like. So on the left are the observations. On the right is the map built by the system. The dark green are the right map predictions, and the light green are false positives. And the blue dot is the long-term goal predicted by the global policy. And so the system can explore any new environment efficiently. Here we are trying to maximize coverage in as a few time steps as possible. And we can just take this modular pipeline and replace this global policy, which is goal agnostic here, with a goal-oriented semantic policy. And now we can do object nav. The idea is very simple. We take the object goal, like a chair, and pass it through the goal-oriented semantic policy. And now we are minimizing the time required to reach this goal rather than maximizing the coverage. So the architecture remains more or less the same, only the reward changes. And now we are building a semantic map. So instead of just a geometric map with obstacles and free space, we have categories for different objects. And this helps the goal-oriented policy learn semantic priors to reach a particular object category. So we can kind of have this modular learning recipe where we basically have the observations from the robot. We pass it through some perception system to build a memory, some map-like representation. Then we have the second module, which is the global policy, which takes the goal as input and this memory of what the robot has seen and predicts a long-term goal. And then we have a local policy that basically takes this goal as input and produces low-level navigation actions. And we have basically followed this recipe over many, many different systems, and I'm going to give you a lot of examples. So this is the first system, Active Neural SLAM. Now we can adapt it to point goal by just giving the point goal as input to the global policy. This was the winner of CVPR 2019 Point Nav Challenge. We can do image goal. Now we have, instead of a geometric map, a topological map. Each node is an image, and we give the image goal as input to the global policy and follow the same recipe. We can do object goal. I gave an example of this already. And we can also do language goal, where basically instead of the object category, now we can give the language as input to a semantic search policy, which searches for the object described in the language. We can also use this recipe for non-interactive modular learning. So, for example, for image goal, instead of training online, we can just train using static video data. And this leads to 10x compute efficiency. And this is the no RL, no simulation model, where we just can learn this model by just passive video data. We don't require any simulation or any active experience to learn this distance function. And similarly, we can do object nav by training with only static map data. And we, instead of learning a semantic goal-oriented semantic policy, we have this potential functions to encode which objects are likely to be found in what parts of the environment. We can also use it for embodied active learning. I will not go into too much detail in this line of work, but basically the idea here is you use action to improve your perception. So you're learning a policy to improve your perception system itself by gathering data in the real world. And this idea has been also used by many other works. So this is not our work, but this paper uses, instead of predicting the map directly from depth sensor, it anticipates unseen parts of the map. They follow a very similar modularization. Perception predicts the map, goes into a global policy, predicts a long-term goal that goes to a local policy. Here's another example of density-based maps. Again, the same kind of modularization. Example of image nav with metric maps. Another example of multi-agent exploration. Most of the top entries on public leaderboards also follow this recipe. This is the top entry on AI to Thor rearrangement leaderboard. It also builds a semantic map and has a global policy to predict long-term goals. The second place system is also following a very similar recipe. The same with the Alfred leaderboard for language goal. So get the idea. So far, I've shown you results on simulation benchmarks like Habitat and AI to Thor. And over the last few years, we have moved from game-like environments to reconstruction-based simulation environments. But the question is, as Jan would put it, does it really work in the real world? We can do a lot of simulation experiments, but we eventually want these systems to work in the real world. And so we did a large-scale evaluation. We literally take the robot, put it in the back of our car, and rent Airbnbs. And every night we go to a new Airbnb, evaluate our robot. We do 10 plus trajectories per home for each method. And we want to compare success rate and SPL, or efficiency of the method. So we have 3 approaches in this large-scale evaluation in 6 completely unseen homes. And these are real homes. These are not lab environments. We have never seen these homes before. We get this home only for 1 day. We do the experiments and go to the next home the next day. And we have 6 goal object categories. And the 3 methods we are evaluating are these 3 classes of methods that I already described. So one is classical, where we have geometric map and frontier exploration. This doesn't require any training. The second is end-to-end reinforcement learning, or imitation learning plus reinforcement learning. We have 77,000 human trajectories for imitation learning, and then we fine-tune for 200 million frames of RL. And our modular learning recipe, where we have semantic map and a goal-oriented exploration policy, which can be trained with just 10 million frames of reinforcement learning. So this is our complete system for object nav. So we take the RGB frame, we do semantic segmentation, take the depth frame, associate the semantic segmentation with each point on the depth input, project it into 3D to get the 3D semantic map, and sum over the height channel to get a top-down 2D semantic map, and then pass it through a goal-oriented semantic policy which predicts the long-term goal. And then we have the local policy or planner to take the low-level navigation actions. And here are the results. So surprisingly, in simulation, all the 3 methods work very similar to each other. But in real world, the results are very different. The modular learning recipe gets us to 90% success rate with an XPL of 0.64 as compared to classical with 80% success rate and end-to-end learning with only 23%. So I'll explain these results, why these numbers look like this. So first of all, let's take a look at an example. So here, all three methods are starting at the same point, and they are asked to find a couch. On the leftmost is our modular learning recipe, and it finds the couch the first. In the middle is the end-to-end learning, and it leads to a lot of collisions and eventually fails. And on the right is the classical frontier exploration. It eventually finds the couch, but it takes much longer. So the SPL numbers reflect the efficiency. So the modular recipe in this case gets to 0.74 SPL, and classical is 0.33. The modular learning itself works surprisingly well in real-world environments with 90% success rate. This is how it looks like. We are asking the policy to find a chair here, and this example I showed earlier, where you're finding a toilet. And so why is the case that modular learning is working better than classical learning, classical methods? And the reason is simple, because the modular learning has these semantic priors of what object is more likely to be found in what parts of the environment. So you can learn the priors that if you are looking for a refrigerator, you go towards the kitchen. If you're looking for a toilet, you go towards the hallway. Well, the classical baseline doesn't have this. It's just going to the nearest unexplored point. Why does end-to-end learning fail? We see it fails in many different ways. It collides often, it revisits the same place, and even if it sees the right object, it fails to stop there. And this is indicative from the sim to real transfer. So the modular learning recipe transfers really well, and the end-to-end learning, while it performs really well in the simulation, but doesn't work well in real world. And to really quantify why this happens, we reconstructed one real-world apartment in simulation and conducted parallel experiments with identical episodes in both simulation and reality. So this is a real-world home. We reconstructed it, put it in the simulation, and now we are starting the robot at exact same places in real world and in simulation, and asking it to find the same goal. So this is an example. On the left is simulation, on the right is real world. We are starting it at the exact same location, and we are asking the agent to find a bed. So the reason end-to-end learning doesn't transfer well is because the end-to-end learning has this first-person camera input, while the modular learning has this map input. And the map input, if you look at it, it's very difficult to tell which map is real and which map is sim. So it's kind of domain invariant. But the first-person camera input has a very large domain gap. Here on the left, the semantic segmentation, for example, fails, and this stove is recognized as a bed. This is because of visual reconstruction errors. But on the right, the semantic segmentation works much better in the real world, and the policy gets to the right goal. And so this is the reason the modular learning actually works better in real world than in simulation, because simulation has this visual and physical artifacts. For example, this is this television. I don't know if you can tell, but this is because the simulation reconstructions don't work super well. Similarly, you have like the physical reconstruction error. There are very narrow pathways in the simulation nav mesh, and this is because of, again, errors in reconstruction. And we actually measured the errors in both simulation and reality, and in fact, they do not overlap with each other. In simulation, the policy fails due to visual and physical reconstruction errors, and there are some exploration failures. But in the real world, the biggest failure mode is depth sensor errors. And the depth sensor errors look like this. So you have this noisy depth, and it leads to closed door, or you have these reflections in the mirror. So this is a bed inside a mirror. So the robot hallucinates a bed because the depth reflects on the mirror. We also applied this modular learning recipe for image goal navigation in the real world, and it works at the same performance as the object goal. And there are two key takeaways. So for practitioners, if you are trying to build a navigation system in the real world, modular learning can reliably navigate to objects with 90% success rate, and according to our experiments. And for researchers, this is very similar to the inductive biases that Jan was talking about. That if the models relying on RGB images are hard to transfer from sim to real, so we can leverage modularity and abstraction in policies to be able to get to real world much more reliably. And at the same time, there is a disconnect between sim and real error modes. You can train your models in sim, but you should always evaluate your models in real world because the ordering of methods in sim doesn't correspond to the real world evaluation. And the modular learning based methods, they basically combine the benefits from both classical and end-to-end learning. They get both spatial and semantic understanding and long-term memory and planning from classical methods, and get generalization and low complexity at the same time by using learning. So I talked about all these different navigation tasks: point, goal, image goal, object, language. And in the beginning, I said we want to build a universal navigation system. So far I have showed you only a navigation system that go to one particular type of goal. They're not multimodal. And they go only to one goal in one episode, which means that they do not have this lifelong nature where they can remember object locations over multiple goals and reuse experience from prior tasks. So this is our latest universal navigation system called GOAT, or Go to Anything. And we are going to use the same recipe, and we are basically combining our learnings from all the different models that we discussed so far. So in GOAT, we have the perception module. This has the instance segmentation, depth estimation, geometric projection, and dynamic instance mapping. And it builds a semantic map of the environment. And it also has an object instance memory. I'll describe this in more detail, but instead of having just semantic categories, now you have object instances. So each object instance belongs to a category, but you can distinguish object instances in the same category. So you can distinguish that this bed is different from this other bed. And you have images associated with each object instance, which means you know that this particular instance on the map looks like this in these different viewpoints. And then we pass this semantic map and object instance memory to a global policy. And the global policy can take in any type of goal, language, image, or category. And it produces, again, a long-term goal, the same modularization, the local policy, and low-level action. So let's talk about the perception system. The perception system is taking the RGB, the depth camera, and the pose sensor as input, passes the RGB through instance segmentation model. We pass the depth through a depth estimation model now to get rid of the depth noise errors. Again, we associate depth and semantic category point by point, project it into a top-down map. And we have a dynamic instance mapping module which will correct for errors in the mapping. So if you see a false positive obstacle from far away, when you go close, you no longer see the obstacle, we'll remove it from the map. And this dynamic instance mapping module updates the map and builds this semantic map and object instance memory. And so this is the overall map representation. You have the semantic map with different object instances, and each object instance is associated with a set of images of that particular object instance from all different viewpoints. And as you can see, we can distinguish different cups here based on the location and appearance, or different chairs, books, and so on. And once we are given a new goal, let's say the large white couch, we have a bunch of objects in our object instance memory, and we have this goal localization module, which will figure out which object instance is referred by the goal. So here, couch 1 is the large white couch, and we have the location of couch 1 on the map. So once the goal is localized, we can directly plan a path to this object and take low-level actions to reach there. And the goal localization module is multimodal, so you can even give it image goals. So you can say, take a picture of a chair, ask it to find the chair. It can localize a particular object instance, like chair 3 in this case, and then again you can localize it on the map. And if you're given a goal which is not there in the object instance memory, we explore. So we keep exploring till we find this object. And finally, we have the local policy, which is just based on analytical path planning. Once we have a goal on the map, we take low-level actions to plan up to follow the path to this goal. Again, we are going to do large-scale, in the wild, empirical evaluation. We have 9 unseen homes, 4 methods, 10 trajectories per home, 5 to 10 goals per trajectory. This in total represents over 90 hours of experiments in real homes. Again, not lab environments. We have over 200 object instances with corresponding image and language labels. We sample randomly from these object instances when we do a lifelong navigation episode. So now you can see the example with the different components. So again, there's the image of the sink. The robot starts exploring. As it's exploring, it's putting objects on the map. Each object is associated with a bunch of images, and as it finds objects, as it finds the goal object, it goes to it. If it has already seen a goal object, it can directly localize and plan a path to it, so it gets more efficient over time as it explores more. And here's another example. So a different chair, a language goal, the green leafy plant, the oven, another plant image, the refrigerator, and so on. In terms of numbers, the full GOAT policy gets 83% success rate with 0.64 SPL. If we remove the memory from GOAT, which basically means after every goal, we reset the memory, so the robot starts exploring again, you have a much lower success rate because of a timeout and a much lower SPL of just 0.19. And then we can have another method where we have GOAT, but with just the category level objects and not object instances. So that achieves a success rate of 49%, and we have the clip-on wheels baseline with 51%. And more importantly, the performance of GOAT improves over time. So in the beginning of the episode, we have 60% success rate, but as you increase the number of goals, and GOAT has more experience in the same environment, the success rate goes up to 90%. But the baseline without memory has a constant success rate of 60% because it is throwing away the memory after every task. And the clip-on wheels baseline also improves performance over time, but the saturation is much lower than what we can achieve with GOAT. And there is an example comparing GOAT with the baseline. So on the left, we have the full GOAT system. In the middle, we have the GOAT without persistent memory. And on the right is the clip-on wheels baseline. So here, all the 3 systems start at the same place, and they are asked to find this image of a bed. In the left, GOAT finds the bed. In the middle, also without any memory, Goat still finds the bed. And on the right, clip-on wheels fails. It finds the wrong bed because of localization failure. And now we can give the um, next goal as input, which is this image of a plant. But you can see that in the middle, the Goat, without memory, the map is reset. So it starts exploring again. And this leads to low performance because it doesn't remember the objects that it has already seen. Goat is platform agnostic. We haven't made any assumptions about the embodiment of the robot. All we require is a simple camera sensor and a pose sensor. Any mobile robot with an RGBD camera and pose can use the system. And we tested it with the Hello Robot stretch system in addition to the Boston Dynamics Spot. So one is a quadruped and the other one is a wheeled robot. We can also chain it with pick and place skills to do mobile rearrangement. Here we ask the policy to first find a bed. So it explores the environment and looks for a bed. Once it finds the bed, we ask it to find a teddy bear and pick it up. So it goes back, picks up the teddy bear, and then we ask it to place it back on the bed. So it can efficiently go to the bed and place the teddy bear there. It can also do social navigation because of the dynamic mapping capabilities. So here we ask the robot to go to a refrigerator, and a person blocks the path through the refrigerator. So it goes around the counter. Then we ask it to follow the person, and it dynamically updates the map, updates the location of the person on the map, and it follows the person as they're moving. So in summary, we have a universal navigation system that is multimodal. It can go to any object specified in any way, image, language, or a category. It's lifelong. You can drop it in any unseen environment and ask it to go to a sequence of goals. It remembers objects in its environment, and its performance improves over time. It can operate in real homes, completely unseen. And it's platform agnostic. You can put it on any mobile robot. We can chain the system with pick and place skills to do mobile rearrangement or to do social navigation around people. So this is a work of a lot of people from Facebook AI Research, UIUC, Carnegie Mellon, and Georgia Tech, and UC Berkeley. And there is more details available on my webpage. Thank you, and I'm happy to take questions.
Thank you very much. Any questions either in the room or online? Florent?
Thanks for the very clear presentation. My question is the following one. You say that, of course, your approach goal is platform agnostic. You also said that, of course, it improves with more episodes because you could use this episodic memory. Have you tried to start learning, your memory, for instance, with one platform, one type of robot, and then, use this representation with other robots to see whether it would still hold or not?
Yeah, that's a great question. We haven't tried this, but I expect this to work because all we need is the localization of the new platform in the old map. As long as you have that, it should work just like the map was built by the new platform itself. Because it's just a top-down map, doesn't encode any robot-specific.
so low, or what do you actually do there? You build the map on the fly, or what's the difference with the modular approach?
So in end-to-end, we just pass in the raw camera observations, and we ask the network to predict low-level actions. The performance is actually very good in simulation environments, but it doesn't work well in real world because of the domain gap between sim and real, and especially the visual domain gap, where the things you see in simulation look very different from things in the real world.
And so you don't have a memory, or you do have a memory?
You have a memory. You have a transformer layer. I mean, so just like a regular autoregressive neural network. We tried transformers and LSTMs.
Yeah, but you don't build up a map.
We don't have an explicit memory, yes.
So you don't have an explicit memory, because that could be also part of the difference, right? That you don't have an explicit memory, which makes, I mean, which we found makes a big difference, right?
Yeah, so what we have tried is building an explicit memory and giving that as input to the neural network. And that still doesn't work as well, probably because it still relies a lot on the visual input. So what we have done in the modular setting is we removed the first person input to the global policy. We only give the the map as input, and the map itself is domain invariant. And this is where we put in our inductive bias, that all the things required for deciding high-level navigation actions are encoded in the map. So we don't really need the first person camera input for deciding the long-term goals.
And to build the modular system, you use other vision components, or you use more information, or
we use
real-world information, basically.
Yes, we use components trained on real-world data, like instance segmentation and depth estimation model, to build this memory.
Okay, so that's where you get the real-world information.
Yes, exactly.
Okay, and
yes.
then one last question: the end-to-end model. Did you try to train it on a few real-world examples and then run it? Or?
Yes, we tried to fine-tune it on the real-world data. I believe we had around 200 trajectories in real world for imitation learning, and that doesn't seem to help at all, because that's very little data for end-to-end learning system.
Okay, thank you.
Yeah.
Thanks for the presentation. The question is actually related to Mistral AI, who was recently on the spotlight with a very large LLM that was on the top of the leaderboard. So can you maybe share on your ongoing or future projects that links to large language model work and at Mistral? And
Yes, so at Mistral we are training foundation multimodal models, and I think that is kind of missing in robotics right now, which is basically human knowledge that is captured on the internet, but we don't have real world active robot data, but there's a lot of human knowledge that is there in videos and text even on the internet that can be used to guide our robots. So we are working on models which can understand video and text.
Thanks.
There is one more question online. What are some open problems in multimodal learning for navigation?
I think there are a lot of open problems. I think in terms of building a system that works in real world, I think if you have a reliable mobile robot and with some engineering effort, you can build a system. But I think there are a lot of open problems in getting these systems to do useful things like mobile rearrangement. I think we showed some examples with cups and teddy bears, but there are many types of objects where you don't, the pick and place still doesn't work reliably well. Like even for common objects like plates, it's very difficult to pick or place plates reliably. So I think there is a lot of work to be done in that space. Yeah.
Okay, that actually also follows answers the follow-up questions of the same person online. That's good on interactions. Is there any other question in the room or online? online a little bit late because I think there's a delay of a couple of, at least 1 minute. No other question? Yes, Jean? I was counting on you, Jean.
I don't see any mechanism, in fact, to abstract from the episodic memory. So if you have small changes, basically your flats are empty, you don't change the furniture and so on. So how you abstract, in fact, from this elementary experience on different flats, so that a new flats, in fact, you have the concept of a kitchen, the concept of a table surrounded by chairs and all this kind of stuff. That's, in fact, it's common sense knowledge. So.
Yeah.
As human, we have hierarchies, in fact, of memories.
Yes.
So you have very basic memory, which is just episodic. So how you abstract from that?
Yes. Okay. So there are two different things. So one is generalizing your visual object understanding over unseen scenes, like understanding how does a refrigerator look like, or how does a chair look like? And that we have vision systems that can do that. So that's what we use, instance segmentation models. And then there's a second thing, which is understanding these semantic priors of how human homes are arranged. Like, refrigerators are close to sinks, that kind of understanding. And this type of understanding we actually get in simulation, where we have around 1,000 homes reconstructed. We have this data set called Habitat Matterport 3D data set, where we basically take Matterport scans from 1,000 real-world homes, put them in simulation, and we can learn this kind of semantic priors from that data. And the way we are able to transfer this from simulation to real world is by working exclusively in the map space. So we go from first-person RGB to this top-down semantic map. And in this top-down semantic map, we are learning these semantic priors that if you're given a goal, find a refrigerator, it will look at the objects already explored and try to predict which direction is the refrigerator, right? And this can be learned because we have 1,000 homes, which are all real homes. And because we are working in this top-down map space, it's domain invariant. It looks very similar in simulation and real world. So we can transfer this knowledge from simulation to real world.
Do you think 1,000 are enough?
Probably not. So we have, using these 1,000 homes, we can beat the classical frontier baseline by about 5 to 10% absolute improvement. But if we have more data, we can do much better. This is only for large objects. For small objects, this is going to be even harder. Like if you have to find a remote control or your keys, you need even more like semantic priors, and this kind of small objects are not captured in the reconstruction. So we don't have much data for these things.
Okay. Any thoughts on reinforcement learning versus imitation learning?
I think both are useful. I think imitation learning, I always kind of think about how humans learn this. A lot of the knowledge for humans comes from imitation learning. Just by looking at other people do things, humans can learn how to navigate or how to find objects. And there is some amount of reinforcement learning involved where you try things, you fail, and then you learn. So I think both are important.
Okay. I have one more question, and especially since you were also involved a lot in the Habitat platform. The reconstruction is really bad, and you showed that. That's not the Habitat problem, right? That's the Matterport scan, which we load into Habitat. But when you look at nerves, it works so well. When do we finally get nerve-based quality reconstruction in simulators like Habitat? What's the problem? Why don't we have that yet?
I think there's no research problem here. It's just an engineering problem that we need to solve. Where basically we can. I think like the main challenge here is like when you have a nerve reconstruction, you don't know what is the plane of navigation or what the navigation mesh. So that needs to be inferred from the nerve reconstruction. And that's a bit of a technical challenge. But other than that, you can load the mesh into Habitat and render it pretty easily using the renderer. This is the only difficulty is figuring out what points are navigable and what points are obstacles in the nerve mesh.
Yeah. Okay. Thank you. Let's thank the speaker again.
Thank you.